Welcome to Data Skeptic Machine Intelligence, our podcast series exploring contemporary topics in artificial general intelligence and large language models. The title of today's episode is going to spoil the punchline completely. The Winograd Schema challenge has been defeated. That's the result of some recent research we're going to discuss today. But in case you need a refresher, we've done it on the show before, but what are Winograd Schema challenges? They're pairs of sentences. And these two pairs of sentences are quite similar. They usually differ by one, maybe two words, something along those lines. Although the difference of that key word can make all the difference in the sentence. Let me give you an example. The city council refused the demonstrators a permit because they feared violence. All right, I'm going to change one word. The city council refused the demonstrators a permit because they advocated violence. And the question is, who does they refer to? And when you say they feared violence or they advocated violence, and that one word change so completely changes the meaning of the sentence that the pronoun they refers to a different party in each one. Well, how do I know that? I know about city councils, I know about demonstrators and the need for a permit. I know the city council would fear violence. I know that demonstrators that advocate violence would likely be denied a permit. I have to put a lot of world knowledge together to be able to disambiguate the they pronoun. And for quite some time, this was an unachievable challenge. The methodologies of natural language processing were not ready to take on the Winograd Schema challenge even just a few years ago. But all that's changed now with the advent of large language models.
So I'm Vid Kocijan, and I'm currently employed at Kumo AI. I have previously, and the work that we'll be discussing today has been done as part of my Ph.D. at the University of Oxford.
And can you share a little bit about what you focused on during your Ph.D.?
My focus has been quite dispersed, but it has been around common sense reasoning, pre-training in large language models, pre-training in knowledge-based completion, and how all of this pre-training impacts various societal biases that models pick up from the unstructured data.
Interesting. So when you're saying pre-training, are you starting from a base model and extending, or are you starting from first principles?
This differed throughout my different projects that I have been working on. In the case of large language models, I have mostly been working with large language models that have already been trained by others. At the time, that was models like BERT or early GPTs, and then do additional training that could still be considered pre-training because it was done on some artificial data. When I was working with knowledge-based completion, my research direction, so I've started from the first principles. I have started from scratch and not foundation models.
Well, in the time you've been studying and working with these techniques, I think it's fair to say the field has been moving very quickly. Do you have any general observations of where or how far it's come since the time you started?
Well, it made a massive leap. So when I was starting my PhD, we have just been slowly moving into this like large pre-trained model phase. So I even remember having discussions with other students or professors discussing whether it's really necessary that we use some pre-trained model instead of just creating one ourselves, and convincing that reviewers that, for example, retraining BERT with filtered out data is not really an option for this experiment. And of course, now we have come to a situation where majority of research, especially in the field of natural language processing, is done on models that have been pre-trained by massive research groups or corporations and are simply out of reach of a regular individual. And so we spend much more time investigating how these models behave rather than train them from scratch over and over again.
Well, when I was studying, and I'm a little bit older than you, so maybe I'm more old school in these ideas, but in NLP, there were lots of schools of thought. Some people thought machine learning and neural network approaches would be good for some problems, and people also thought that something like common sense reasoning, maybe it wouldn't be good for that, that we need a more symbolic approach or something along these lines. That opinion is probably less popular today than when I was in school, but it's not gone. Do you have any thoughts on it?
I dare say that this still can be a hot topic depending on whom you ask. My personal take on this is I do not think that language models as we know them right now can completely solve the problem of common sense reasoning reliably. That being said, I wouldn't be surprised if it only took minor modifications or, combining it with something that brings a significant improvement. Or depending on the development, maybe we'll see a completely different direction in the future. Though given the success of large language models at the moment, I would be very surprised if they were replaced very fast. So I feel like for the foreseeable future, and in AI that's not a very long time, I think will be simply centered around LLMs. And regardless of how ingenious alternative approaches become, LLMs are currently getting so much development and have such a leeway compared to all other methods, simply in the matter of like scale and engineering hours, that they will remain on the top place, like the number one approach for all problems in NLP for quite a while.
When did you first encounter the idea of the Winograd Schema challenge?
The idea of the Winograd Schema Challenge was brought to me by my supervisor, Thomas Lukasiewicz, who really wanted to see progress on it. It was also at the time, so this was in I think 2017 and 18, it seemed exactly like a kind of a problem that neural networks cannot solve. So, of course, methods based on logic and reasoning didn't solve them either at the time. But at least there was a theoretical chance that if we have the right background information and if we have good enough information extraction, that then we know that it is theoretically possible to solve them. Whereas with neural networks, it was a big unknown. How these develop, we have seen. Currently, it's LLMs that ended up solving the problem, but this is what made the problem truly interesting at the time. So this is how we started working on it.
And would you mind providing an example of maybe one of the pair sentences so listeners can get some perspective on what WSC is?
Probably the most well-known example that is often displayed is the pair of sentences, the first one being, the trophy didn't fit into the suitcase because it was too large. And the second pair of sentences differs only in a single word. The trophy didn't fit into the suitcase because it was too small. The challenge itself is to correctly resolve the pronoun, in this case, it, that appears in the sentence, and changing the words large into small changes what the pronoun refers to. More specifically, when we say the trophy didn't fit into the suitcase because it was too large, it was the trophy that was too large. But when we say the trophy didn't fit into the suitcase because it was too small, it was the suitcase that was too small. It's an ambiguity in English language that human listeners resolve by their background knowledge and common sense reasoning. And it is this ambiguity in English language that Terry Winograd described in his thesis in 1972 as one example why processing English is hard. And this served as the basis of the Winograd Schema Challenge as devised in 2010, collecting a collection of such examples and using NLP systems for coreference resolution to see whether they can resolve them correctly as a test of their ability to perform common sense reasoning.
If I were tasked with coming up with some example pair sentences, I think I could do it. My brain is capable of making up new ones, but I think only at a rate of maybe 4 or 5 per hour. They're kind of tricky to come up with. What kind of data sets are available?
During this time, quite a lot of datasets were created. There is one which is considered the golden standard. So that is the original collection created by the creators of the challenge. It's simply known as under the name the Winograd Schema Challenge, or sometimes WSC and then the number 273 for the first 273 examples. These were created manually by the creators, mostly Ernest Davis, but not himself alone. And a lot of effort and care went into them. So he would make sure that both of the halves of the Winograd schema were meaningful, that were resolved correctly, that were not obvious. So, for example, that they could not be resolved with something like watching which words often co-occur together. This was named as a Google test. So if it appears often together in Google, then and the other option doesn't, then it's probably not challenging enough. One interesting condition that was apparently not he did not pay a lot attention to, or at least he paid a lot of attention to it when creating schemas, but they did not pay attention to it when writing, for example, the instructions or papers, was that these should read naturally. Because at the time, when they were writing them, it seemed obvious that you should only include sentences that read naturally. But as with other datasets that were later created, this was often one of the requirements that was the hardest to meet. The problem with this manual creation by experts was that it is ridiculously slow. It took he was creating them, 3 per hour or so. For a good and comprehensive test, you need a large collection. So multiple researchers then tried to create other collections of Winograd schemas, either with different methods to increase the scale so that they would be able to also do some training, or with different goals in mind entirely. For one of the earliest attempts was definite pronoun resolution, where the authors have simply asked a bunch of students, giving them homework, write 30 examples each and send them back to us. Of course, the students did not put that much care into these schemas, but they still read very naturally. More recent examples, and the largest so far, for example, would be Winograd, where they have used online crowdsourcing platform, Mechanical Turk, and were able to create tens of thousands of examples, but of course at the cost of quality, or at least naturalness. One direction that I quite liked myself are datasets like WinoGender and WinoBias, where they try to take advantage of this ambiguity in English to assess models for gender bias. Other types of data sets people have created out of the original idea of the Winograd Schema Challenge were, for example, data sets of explanations, where models should also be providing or at least choosing an explanation for their prediction. Or one that is also particularly interesting is so-called Winograd dataset, where they have turned this into a challenge in visual reasoning. So given a picture, match the caption. For example, you have a picture with some plants surrounding a light bulb and a picture of a light bulb surrounding some plants. And you've got to match which one is which. Just recognizing what is in the picture is not enough. You actually have to be able to understand the relation of the objects on the picture and how they relate one to another. But this one is also the furthest from the original because it's called Winograd, or it has relation to the Winograd Schema Challenge because it has this ambiguity, but it doesn't actually have coreference resolution as part of it. It's only, so how to put it, it's only loosely inspired.
When you think about the challenge, it's essentially asking a 50-50 question. So I guess we would say the baseline would be the toss of a coin. But is that fair? I feel like if I use some ancient NLP technique like just term frequency, inverse document frequency, TF-IDF ought to get me somehow, better than chance. What's the floor? Or do you have an opinion on roughly where the floor is?
For a very long time, researchers were unable to get beyond or like significantly above 50%. So the 50% is, of course, the basis that you can always get with random guessing. The problem is this property that it is a single word that makes a difference, that changes the meaning. It makes the whole system very susceptible to mistakes based on either incorrect information extraction from the sentence or a little bit of noise in background knowledge can cause incorrect deduction. Until the arrival of large language models, there were very, very few attempts that would be statistically significantly better than random guessing.
Is there any point at which that started to shift? Did something like Word to Vec or BERT get us a little bit of the way there, or did we just have to wait for large language models before progress could be made?
It was BERT. Well, it was also already possible with GPT. I was able to get intermediate results, like statistically significant results with GPT, but it was with BERT that we got some really significant improvements. So to be fair, there have been successful attempts before with models, language models trained from scratch and just pre-trained a lot. I believe that there was an attempt that got to 62, I think, percent just by combining an ensemble of different language models pre-trained on different pieces of text. But then significant boosts in performance were basically pushed by two factors. The first one being, and the main one being, the models being ever larger. The second one more data being available. So that is when larger data sets of Winograd schemas, such as Winograd, were released, the performance naturally improved. Many authors, including my own research, we have tried to fake or create fake data by modifying sentences or taking some common sense reasoning out of various knowledge bases and similar. But in the end, it was these tricks that gave us some additional boost only resulted in like 2 or 3% performance boosts. And it was crucially the scale, both in actual Winograd schemas, but more importantly in pre-training, that led to the actual solution of the challenge.
And then could we talk about that resolution? We've commented a little bit that the schema challenge has been passed. What does that mean? What is the metric of success?
Originally, the idea was that if a model can resolve 90% of the cases, it would be considered human level. To be completely honest, really rigorous human testing has never or has not been really performed, so we can't really say what the human level is. But given that many of the sentences were either from natural texts and then transformed a bit to fit the criterion, or were agreed upon by often many readers that they read naturally, it would be meaningful to expect that human performance is above 90%. And this is also why the expectation so it was at 90% that the bar was set, where it was expected that, if the model is 90% accurate on this, we can claim that it's solved. So alternative metrics did arise later on when people, for example, additionally wanted to investigate consistency, so that models should not only be solving 90% of overall examples, but 90% of pairs, so that it reliably solves both instances, both with a swapped or non-swapped word. But because I don't feel like these changes in evaluation made any particularly significant difference to the interpretation whether the challenge was solved or not. Because after all, for example, if you resolve 90% of the cases, you're basically guaranteed to solve 81% of halves, even if your model is not actually consistent. So as such, additional alternative approaches to evaluation mostly just push the score a bit lower, change the bar a bit, but that bar has been picked somewhat artificially in the first place. So
Have you seen that large language models are consistent from run to run? If they get one answer correct, do they always get it correct?
from run to run, as in being asked the same question again, or being asked one and another Winograd schema challenge half.
And then you'd mentioned like 90% being that threshold. And I think, that's a good one that sounds about what human performance might be, even if there's no rigorous test. But I'm curious if maybe things like that accuracy we would label as necessary but not sufficient. I like to think about p values. I don't think there's anything wrong with them. I like them, but they don't tell the full story. There are other things one needs to consider. Are we evolving beyond some of the traditional metrics of success?
I feel this is very much an open question, because this is also basically one of the conclusions or larger lessons that we got out of the Winograd schema challenge, and that is the fact that a model was able to resolve this challenge with 90% accuracy didn't really tell us much about the model. It was not a proof of anything. And one of the takeaways that we write about in the paper is effectively that this should be kept more in mind, so that we are not only designing metrics that are easy to evaluate, but metrics that give us conclusive results that might confirm some hypothesis or might serve as a proof of certain value or certain ability. And this is hard, especially in areas such as common sense reasoning, where often people stumble already on definitions, and you get various different definitions of what exactly common sense reasoning is. I am looking forward, and I do hope that more interesting new metrics will be proposed in the future, but I'm not bold enough to claim that I have an answer here.
Well, what is the current state of the art relative to that 90%?
There have been multiple models that got, say, 90, so 95, I think, percent. But more importantly, once the original collection of the Winograd Schema Challenge was solved, people mostly stopped evaluating on it. That collection was created out of 285 examples, and results above 90% are no longer statistically like significant or conclusive. So it's, saying effectively 1% of a difference means that you solved two additional or three additional Winograd schema halves, which can be very much just due to random deviation. So I very much do agree that once that by a point of 90% has been passed, there is no reason to do future evaluations. There have been more experiments done on Winogrande, which is a bit larger. So that example does have a few thousand examples in the test set. And but there again, I think what happened is one result got over 90, then the interest in that dataset and problem sort of dropped.
Well, one concern that I think some people could have is that these large language models, they've been trained on these huge corpora of data. We don't even know totally what's in there. What if the actual Winograd Schema Challenges data set somehow is in the pre-training and the large language model is just overfitting and memorizing it?
This is actually a very valid concern. So it's hard to say. Fortunately, many of these evaluations have been done on held out datasets. So, for example, when models have been evaluated on Winogrande dataset, which was introduced much later and has not been, and instances were not discussed like broadly and introduced as high points and examples. Those were mostly new examples, and yet the models were still able to solve them. So I do agree that this is genuinely an issue with the original collection, where many of the original instances have been displayed, just like at the beginning of this discussion between the two of us, and discussed why exactly they're hard. And yes, the training data of large language models can be considered contaminated with this information. But then this is why new datasets are created with new holdout examples, and those have been solved as well. So we have a way around it, and that is, create new instances.
Well, when I first learned of the schema challenge myself, I was impressed with it by its challengingness. What I knew about NLP, I didn't have a clear path for, oh, this will be solved quickly using techniques X, Y, and Z. I was personally a little bit surprised that large language models could accomplish this. And maybe I was also surprised when AlphaGo beat Lee Sedol. There are these challenges where machines are hitting milestones. Could you remark a little bit on how much of a milestone this is? Is this a major trophy for computer science or just one of many?
I would dare say that it's one of many. It is important in the sense that this was often displayed as an example of thing that cannot be done with the existing technology. So it was shocking or sobering when language models have gone in effectively a matter of 2 years from 60% performance. And even that 60%, if I recall correctly, there were some minor issues raised about it, to undeniably solving it over 90%. It was shocking in this respect, but I would not consider it a massive milestone in the same way, for example, autonomous driving would be, simply because the fact that we now are able to solve the Winograd schema challenge doesn't really it doesn't really have like profound impact on future directions. It's not like this opens some new gates. We have simply demonstrated that something that we thought was incredibly hard is not actually incredibly hard, but this incredibly hard problem is not something that we would meet on a daily basis, and it does not open the doors for other important problems in natural language processing or AI in general.
Could you expand upon that? I think the remaining big challenge is the imitation game, Alan Turing's famous Turing test, which is for sure harder than Winograd schema challenges. Are we closer, or did we just have a local win?
Well, whether the imitation game is harder or whether is still open is, I feel, very much up to discussion, because the Winograd schema challenge has been in fact introduced to replace it, because it has been solved, or at least claimed to be solved, in 2000 in was it 2012 by Eugene Gustman. The problem with the imitation game is primarily that humans are, not great judges. We get fooled very quickly, and this is exactly how Eugene Gustman, so that AI model that was claimed to solve the imitation game first, the model effectively fooled evaluators by getting them to talk about themselves. This is also why Winograd Schema Challenge was considered so interesting, and that because it was very unambiguous to evaluate. With that respect, I would say the imitation game is as hard as the judges are good. And I feel like the imitation game is much harder in 2023 than it was in 2012 or 2013, simply because people are more used to AI systems and would be better at determining whether something is an AI system or not. But that being said, I do feel like human judges are still subjectively susceptible to same sort of emotional manipulation or tricks that allows them to be tricked into thinking that the person they're talking to is human, even if it's not.
Yeah, I think we're going to have to start talking about, 8 out of 10 people rated this human or rated it a bot or something along these lines. There's a lot of variance in judges.
Well, I don't see a reason. So original Turing's bar that he set was 30%. I don't see a reason why to go above 50. Even 50 is probably too much because 50 effectively says you're tossing a coin.
I can't tell. Yeah.
Yeah, if you're talking to two humans, you'd probably ideally get 50% because the judge would effectively be guessing. Yeah, that being said, it would probably take more than just a five minute of conversation that Turing initially envisioned to properly determine whether the agent that you're talking to is genuinely intelligent. Simply to try and remove that factor of some sort of emotional manipulation or trickery that tricked judges in 2012.
Well, does that leave us without any test for measuring whether or not a machine bears the property of artificial general intelligence?
I don't think we have a general test at the moment, but this is not a reason why we should stop designing them. It's actually great that we are actually forced to truly think what is it that makes an agent generally intelligent rather than relying on some sort of proxy tasks such as resolving pronouns or chatting for 5 minutes. All of this challenges, both the Turing imitation game and the Winograd Schema challenge, basically suffer from the same issue, and that is they're not conclusive. The fact we have seen, in 2012, nobody thought that that model that fooled the judges was generally intelligent. It was simply, very good on playing on the judges' weaknesses. And similarly, nobody thinks that the first model that resolved the Winograd Schema challenge has common sense in its entirety. It's probably actually the best moment right now to start thinking not what GPT-4 or whatever cannot do, but rather what would it take to convince us that it is generally intelligent, and then start from there and work backwards into, okay, how to design tests for it.
Well, for people who, let's say, were putting a lot of effort and energy into trying to defeat the Winograd Schema challenge, now that we find it defeated, what are some of the new challenges researchers like that will take on?
Quite a lot of benchmarks have been created on common sense reasoning. None of them became this, how to put it, popular or captured the popular mind. But there are quite a few collections of problems that remain, how to put it, unsolved or not solved reliably. So mostly, for example, describing social situations and knowing how to respond or what is a meaningful response, and, and similar. But at the moment, I would prefer to avoid pointing out one single problem as if it was some sort of a crux, simply because we have this benchmark inflation. Effectively, each problem that we are coming up with, GPT X plus one, that is able to solve it. And then we realize that, okay, it's great that it solved it, but it's still flawed in one way or another. And then we keep creating new sort of benchmarks that get solved without a real effect. It's easy for me to say, yeah, we need new benchmarks that will have conclusive results because I cannot even list one as an example, at least not in common sense reasoning. But this is some sort of an ideal that, some sort of a moonshot that we would ideally be looking for.
I think it would be hard to deny there's been major advancements in NLP. The defeating of Winograd Schema Challenge is just one of them. Are we approaching a point when you think we will hit AGI, or are we on some asymptote where these improvements will get better but never quite deliver that?
I will intentionally avoid answering this question, mostly because I don't have a good estimation of what AGI would even mean. So I feel like it's a question where unavoidably the answer depends on what some sort of your philosophical definition of AGI means and what would it take to convince you as the individual that something is generally intelligent. As such, I don't really have a good answer. My personal take on this is I do not believe that models such as GPT with fixed number of operations can be considered generally intelligent simply because they're inherently limited in how much reasoning they can do. And they don't have long-term memory. They're limited by a certain span of text that they can keep in their memory, but that has been increasing. Beyond pointing out obvious flaws in the existing models, it would be hard for me to determine what it would actually take, because sometimes it turns out that it's only a small piece, or sometimes it's something fundamental. And I'm not a philosopher, nor am I a neuroscientist to tell what is it that it's missing to our mathematical models that would make them intelligent.
I wish I could ask one and have the answer. I agree with you there. There's a lot of open questions here that I'm eager to hear future thoughts on. In any event, where can listeners follow you online?
I personally prefer not to be followed online too much. I
Sure.
do have a Twitter account, but I don't really post regularly except occasionally for when I publish a paper. I'm perfectly happy to not be followed.
All right, sounds good. Well, thank you so much for taking the time to come on and share your work.
Thank you a lot for inviting me.